Hello, welcome to this lecture series on chemical kinetics. In this lecture I am going to discuss about Arrhenius equation and some of the features of Arrhenius equations. Okay, let's get started. In my last lecture I have told you that in most of the chemical reactions, okay, in most cases means chemical reactions, as temperature increases, rate of the reaction increases. Okay, this was found experimentally. As temperature increases, rate increases in most of the reactions. And it was also found that in gas phase reactions, chemical reaction occurs due to the collision between reactant molecules. Okay, so only collision is responsible for chemical reaction in gas phase reactions. Okay, and it was also found that when temperature increases by 10 degrees Celsius in the case of gas phase reaction, okay, number of collisions increases by 200 to 400 times. Okay, if collision alone is responsible for reaction, then the expected increase in the rate must also be 200 to 400 times. But the actual increase in rate is 2 or just 3. It is not 200, it is not 250, it is not 300, it is just 2 or 3. Okay, this surprising result, okay, made the scientists to think upon other factors, if at all any factors available, okay, how that factor affecting the rate of the reaction. So people started to think on that direction, right? Scientist Arrhenius, he did extensive research on the effect of temperature on chemical reaction, a rate of chemical reaction. So Arrhenius, he carried out, okay, extensive research on the effect of temperature on the rate of chemical reactions, okay, and he found that when ln k, natural logarithm of rate constant, when ln k is plotted against 1 by temperature, he got straight line for many reactions. Okay, straight line with a negative slope. If any chemical reaction gives straight line with a negative slope in the plot of ln k versus 1 by t, okay, we can call those reactions as Arrhenius reactions. Arrhenius reactions. I repeat, what is Arrhenius reaction? If any chemical reaction gives a straight line with a negative slope in the plot of ln k versus 1 by t, those chemical reactions can be called as Arrhenius reactions. Why I am giving this point? Because there are non-Arrhenius reactions also available. Okay, let us first discuss about Arrhenius reactions, then we'll discuss, right, regarding the non-Arrhenius reactions. Now see here, this straight line has an intercept and it also has a slope. Okay, so you know very well the general equation for a straight line is y is equal to mx plus c. Okay, now in the place of y I'll put ln k, and in the place of c, right, this c is nothing but the ln k, where k has the maximum value, right? So this is nothing but ln k max, right? This ln k max, Arrhenius gave a symbol for this, that is plus ln. He replaced that k max by a term called a, ln a. Ln a is nothing but y-intercept. So a is nothing but maximum rate constant that is possible for a given chemical reaction. Okay, ln a. Then there should be some see in the place of x we should put 1 by t, and there should be some slope. He gave a symbol for that slope. The symbol is this. Since it is a negative slope, so this slope should be minus EA by R. Why EA by R we'll discuss as we go along. So you can write this as ln K equal to ln A minus EA by R into T, or 1 by T. Okay, what does this indicate? Why he introduced the term EA here? Okay, what is the meaning for EA? Yes, we'll discuss that. This equation is what we call as Arrhenius equation. Arrhenius equation. Ln K equal to ln A minus EA by R into 1 by T. Okay, what is EA? What is A? Yeah, I'll give the terms in the next page. But before going to that, this equation can also be written in a simplified form as, see, ln K equal to ln A minus EA by R into T. Okay, this is the Arrhenius equation. I'll bring this ln A to the left hand side. So we can write ln K by A, because ln K minus ln A, if you apply logarithmic formula, log A minus log B is log A by B. So ln K by A equal to minus EA by RT. Then what is K by A? If I remove this natural log, then you should write this as e power minus EA by RT. Okay, or I can say K is equal to A into e to the power minus EA by RT. This is a modified form of Arrhenius equation. So this is also called as Arrhenius equation. K is equal to A into e to the power minus EA by RT. Right? Here we have an exponential term, and before that we have a term called pre-exponential term. Okay, so what is K here? K refers to rate constant of the reaction. And what is A? A is called pre-exponential factor. Pre-exponential factor. Okay, and what is EA? EA is nothing but activation energy, or energy of activation, right? It's nothing but activation energy of the reaction. Activation energy, right? Which is given in joules, joule per mole unit. Joule per mole unit. Okay, and R is nothing but gas constant. Gas constant, and T is the temperature. T is the temperature in Kelvin unit. Okay, now we'll discuss how this Arrhenius equation, okay, gave explanation for the discrepancy that is observed before. Okay, yes, let's proceed further. Before going to discuss that, I'll make one point here. For Arrhenius reactions, what is meant by that? Any chemical reaction, if it gives straight line with the negative slope in the plot of ln K versus 1 by T, we call those reactions as Arrhenius reactions. For Arrhenius reactions, activation energy and the pre-exponential factor, okay, we call them collectively as Arrhenius factors or Arrhenius parameters. We call them as Arrhenius parameters, and these two Arrhenius parameters are temperature independent. They are temperature independent. Okay, so for Arrhenius reactions, EA and A are temperature independent. Keep that in mind. Now what happens? So what's the reason for this EA? Observe this carefully. K is equal to A into e power minus EA by RT. Okay, this is Arrhenius equation. Suppose if EA is 0, suppose if EA is 0, EA0 means this become 1, so K becomes equal to A. And this A, okay, this A is nothing but K max. K max, that is the maximum rate constant possible. What does it indicate? It indicates that all collision gives all collisions are fruitful collisions. I repeat, listen, any reactant molecule, if they collide, they form product. If activation energy of the reaction is 0. Okay, but what is observed is that all collisions are not all collisions, right, are fruitful collisions. I repeat, see, if EA is 0, K should be equal to A. What is K? What is A? A is nothing but maximum K, that is maximum rate constant possible for the chemical reaction. When we'll get the maximum possible rate constant? If all collision leads to product, you'll get maximum rate constant. Okay, if this is true, yes, definitely we should get the increase in rate 200 to 400 times on increasing the temperature by 10 degrees Celsius. Okay, if this is true, see, if EA is 0, then the expected increase in rate, right, then the expected increase in rate, okay, is observed, may be observed, right? But in most chemical reactions, right, in almost all chemical reaction, activation energy is required. Some activation energy is required. Okay, therefore let me go to the next page. So what does it indicate? It indicates that for most reactions, activation energy is not equal to 0. Some activation energy is required. Okay, it means that suppose I have two reactant molecules. If they have energy, right, less than the activation energy, if the molecules have energy less than activation energy, if these molecules collide, that collision never give any product. Okay, no product. So which collision will give product? If the reactant molecules have energy equal to or above activation energy. If it is equal to or above. If the reactant molecules have energy equal to or greater than activation energy, when these reactant molecules undergo collision, yes, they'll give product. Okay, so that is the reason why when we increase the temperature by 10 degrees Celsius, the actual increase in rate is just 2 times or 3 times, because not all collisions are active collisions. Okay, not all collisions are fruitful collisions. Only some collisions are fruitful collision, because for those collision, the energy of the reactant molecules, right, may be equal to EA or above EA. Is this clear? Right? So Arrhenius gave explanation for the observed rate in a manner that, see, this pre-exponential factor, suppose assume that the pre-exponential factor is responsible for collisions. Okay, that will take care of number of collisions. Then we need to find out what fraction of molecules, okay, among the total, what fraction of molecule have energy at least EA or above EA. We can also call it as the active molecules. So we need to know what is the fraction of active molecules present, okay, at temperature T. Right? This factor is nothing but e power minus EA by RT. E power minus EA by RT gives you the fraction of active molecules present at temperature T. Only active molecules, if they undergo collision, you will get product. Okay, so this is the meaning for the Arrhenius equation K equal to A into e power minus EA by RT. Right? The term A will take care of number of collisions. Okay, and this term will give you the fraction of active molecules present, right, in the at temperature T in the reaction mixture. Is this clear? So that means not all collisions are fruitful collisions. This is the statement made by Arrhenius. Not all collisions are fruitful collisions. Only collisions having only some collisions in which reactant molecule having energy at least EA or above EA, only those collisions, right, will give product. Okay, that is the reason why there is no increase in rate by 200 to 400 times. The increase in rate is just 2 or 3. Right? Now, suppose, so this is the Arrhenius equation. Suppose if a chemical reaction, okay, doesn't give a straight line in the plot of ln K versus 1 by T. In the plot of ln K versus 1 by T, okay, I have a chemical reaction which gives a curve like this instead of straight line. We call those chemical reactions as non-Arrhenius reactions. Non-Arrhenius reactions. Okay. Let us assume that for particular non-Arrhenius reaction, okay, A is temperature independent. What is A? Pre-exponential factor, which is temperature independent. But EA is temperature dependent. In this case, yes, you can calculate activation energy by making use of Arrhenius equation. How? Still we can calculate activation energy. How? The formula for Arrhenius equation is K equal to A into e power minus EA by RT. Now, activation energy is temperature dependent. So what we should do? I'll take logarithm. So ln K equal to ln A minus EA by RT. Right, now differentiate this equation with respect to temperature. So d ln K by dt equal to, here I have assumed that temperature A is temperature independent. Therefore, if I differentiate this with respect to temperature, you will get 0 minus EA by R, and we have 1 by T. If I differentiate with the temperature, 1 by T will give minus 1 by T square. Right? See, what we'll get is d ln K by dt equal to EA by R into T square. Or what is EA? EA is equal to RT square into d ln K by dt. Okay? Yes, this is the equation. By making use of this equation, you can calculate activation energy for non-Arrhenius reactions. Okay? Yeah. We'll continue this discussion in the next class. I stop here. Thank you.